In this video, I want to take a look at another class of equations called exact equations that have an analytic solution method that I'm going to go through and teach you guys. I want to start by just looking at an example because the idea of an exact equation is a little bit tricky to get your head around at first. So let's start with an equation, an example. Let's consider the following. So consider the equation 2x plus y squared plus 2xy times y prime. So that whole thing is equal to 0. So here's our big, ugly equation. This equation turns out to not be separable. You can go ahead and verify that if you want to try to do the algebra. It's certainly not linear, right? We have a y squared here. We have a y times y prime term. And inverting it, so basically taking the reciprocal of the whole thing and trying to solve for dx dy, or using dx dy instead of dy dx, also isn't going to give us any useful information. So is there anything else we can do? Well, obviously, I just told you we're going to do something called an exact equation. So consider the following based on this. So right now we've got this equation, this mysterious equation. I want to give you something that's going to be related to the solution and kind of go from there. So consider the function that looks like this. I'm going to call it psi. This is the Greek letter psi. It looks literally like a psi, the weapon like Raphael from Teenage Mutant Ninja Turtles has. And psi is going to be a function that's dependent on both x and y, with the additional assumption that x is a function, or sorry, that y is a function of x. So we have our function psi, that's a function of x, and y, where y is a function of x as well. And here's the one that I'm going to write out. I'm going to do x squared plus xy squared. So how is this related to what we've got up here? Well, if we start taking derivatives of psi, we're going to have to basically take derivatives with respect to x. And I want to also take a look at what happens if we take a derivative with respect to y. So this is some stuff that happens in Calc 3. So for those of you that haven't taken Calc 3 or aren't currently taking Calc 3, this is the one section where we're going to kind of steal a few ideas from there. But luckily, they're not too bad. So a quick side note, I want to compute, we want to compute derivatives with respect to both x and y. And this requires some tools from Calculus 3. And this tool is called, or is something called a partial derivative. The idea of a partial derivative is that if you have a function that's a function of both x and y, you can take a derivative of that function with respect to x, but you aren't really taking the whole derivative because there's this other dependence that it has on y. Similarly, if you have this function that's a function of both x and y, you can take the derivative with respect to y, but again, that's not really the whole derivative because the function is dependent on both x and y. And so a partial derivative is a derivative with respect to just one of those variables. And the way that we're going to notate this is as follows. So we're going to write something that looks like this, d psi dx, but notice these d's look a little bit different than the way that I normally write d's. These are the symbols that we use when we're taking a partial derivative. You don't really need to worry about this until you get to Calc 3, but the idea is this symbol is in place of writing d psi dx like this, where I write my d as like this. It's just meant to be an indication, a visual indication when you see it that, hold on, x isn't going to be the only variable that this function psi depends on. And that's all this is meant to do. So if you have a function that's a function of multiple variables and you take a derivative with respect to one of those variables, so in this case x, it's called a partial derivative. This is what the notation looks like. I'm going to erase the other one so it doesn't look like that. And you will also see this written as using subscripts. So you might see this instead of using primes, because I can't do psi prime. Prime is ambiguous in this case if psi is a function of both x and y. So instead we make it clear which variable we're taking the derivative with respect to using a subscript. So psi sub x means the derivative with respect to x. So this is the notation. And similarly, we'll do the same thing for the derivative. Let's try to write that a little more clearly. The derivative with respect to the y variable, which I could write like this with a subscript of y down there. So this is, again, just strictly notation. That's all you need to recognize is when you take a derivative with respect to just one of the variables, you can write that variable as a subscript of the function's name. But all you have to do to take these derivatives is take them as you normally would. In this case, I'm going to take a derivative with respect to x, and anytime I encounter a y, I'm going to treat y as though it were a constant. Basically, I'm going to say the y, as far as x is concerned, y is a constant. Similarly over here, when I take a derivative with respect to y, as far as the y is concerned, x is a constant. So let me show you what I mean when I say that. I'm going to take some derivatives of this function. The first one I'm going to take is the derivative with respect to x of this psi that we defined up here. So it's easy. Let me just write it this way. We're doing d dx of the whole thing. Let me write it out. X squared plus xy squared. So that is our function psi. When we take this derivative and it hits this x squared, that's easy because the derivative is being taken with respect to x anyway. So what's the derivative of x squared with respect to x? Well, that's 2x. And then I hit the second term, and the second term involves both x and y. What happens to the derivative, this partial derivative operator, when it hits this combined function that involves both x and y? Well, as far as this is concerned, it's going to see this x part, and it's going to treat anything else, this y squared part, as a constant. So what happens to a constant when you take the derivative? It just kind of sifts through, and I'm really just going to have plus this y squared. The derivative doesn't even affect it. And we're just going to have our derivative hitting the x portion of that. So it's going to hit this part here and leave this part alone as though it were a constant. So what's the derivative of x with respect to x? Well, that's just 1. And we wind up with 2x plus y squared for that partial derivative, the derivative with respect to x. Let's do the same thing here for the derivative with respect to y. So let me just copy the whole thing down. Same thing, this derivative is going to hit each of these parts separately. So when I take the derivative with respect to y of x squared, well, as far as y is concerned, this x squared is just a constant. And what's the derivative of a constant? 0. And then the derivative with respect to y is going to hit the second term that involves both an x term that it's going to treat as a constant. So it's just going to pull that x term out. And then we'll have the derivative with respect to y of the remaining part, which is just the y squared. And that'll give me, so the 0 I'm not even going to bother to rewrite, but just x times whatever the derivative of y squared is with respect to y. So what's the derivative of y squared with respect to y? Well, in this case, the 2 just comes down. It's just power rule, and we just get 2y. So I have x times 2y, which I might rewrite as 2xy. And notice that these two pieces that kind of get spit out of these two different partial derivatives happen to be the pieces that show up. Let me do it with some color here. So this piece right here happens to be this piece right here. And this piece right here happens to be the same as, oops, I guess I didn't need to do all of those. Let's do the last part here. That part there happens to be the same as this part here. The only part that we haven't accounted for in the original equation is this y prime term. Okay, so there should be some hint that this function psi is somehow connected to this, but how so? So what is the connection? Well, notice the original equation is written implicitly, right? There's functions of basically x and y all jumbled up, all mixed together. We have an implicit representation of our function here. We certainly haven't solved for y prime all by itself on one side of the equal sign. We've got a a big, nasty implicit equation. It turns out that the process that we just looked at that's going to yield to, or eventually yield this function as part of our solution, has to involve taking derivatives with respect to both x and y. And what that ultimately means is we're going to be taking an implicit derivative of this function over here. So this result that we get here is related to the idea of taking an implicit derivative. So the whole idea that connects the function psi that we just defined, that psi of x comma y, to the original ODE is implicit differentiation. Okay, so let's just do a quick review on implicit differentiation now that we've introduced this little side topic. For those of you in Calculus 3, again, this should be fairly familiar. This is pretty stuff you learn pretty early on in Calc 3. If you're taking it this semester, you've probably already seen something related to this idea at this point in the semester. And then let's do a quick review of implicit differentiation to tie these two different ideas together and back to the original idea of an exact equation. So we've got all these working pieces. And so we're going to concentrate on each one individually and then try to see the big picture kind of when it's all said and done. So let's just talk about implicit differentiation. If we have a function like we had a minute ago, this psi function that we're talking about. So let's just look at implicit differentiation just real quickly as sort of a quick review. Let me do this as a side note as well. Did the last one as a note? Let's do this one. So implicit differentiation review. Okay, if we've got a function, psi, and that psi happens to be a function of both x and y, and furthermore, we make it extra abundantly clear that in fact it's a function of x comma y, but that y itself is also a function of x. So I'm going to use all of these interchangeably. Psi, without writing its dependence on both x and y, we're going to just assume when you see psi in this course, it's a function of both x and y. I may write it like this sometimes, or alternatively, I may make all of the dependencies totally clear and make it clear that psi is a function of x and y, but even the y that psi is a function of is itself a function of x. So ultimately, at its very base, the ultimate dependence of psi is on x, even in the way that it depends on y. What this means is if I want to take a full derivative, and notice I'm back to using regular d's, if I want to take d psi dx, which is distinct from this little rounded d version of d psi dx. This is the partial derivative. This is going to be the full derivative. What you have to do is relate it to the idea of essentially implicit differentiation, or relating it to the idea of a differential that can depend on multiple different variables. But the idea is I want to take basically d dx of psi, that's a function of both x, and y, which is also a function of x. So here's the big derivative that I'm attempting to take here. When we take a derivative, what ultimately happens is we have to take the derivatives with respect to both basically x and y. And so what this is going to wind up looking like is the following. We'd write basically the first partial derivative, d psi dx, times dx dx, and I can write that with regular d's. As may not be clear to you why, but that's not totally important. And the second part is d psi dy dy dx. And I can write these parts with the regular d's because x is only a function of x, and y, as we've seen, is also only a function of x, whereas I have to write these with the little curly d's because both psi is a function of both x and of y. So this is sort of the Leibniz notation. Obviously, dx, literally the derivative of x with respect to x, that's just 1, so we don't need to worry about this piece. These are the pieces, the partial derivatives we just defined a minute ago. So psi sub x, this one over here is our psi sub y. And this piece right here, dy dx, is our y prime term. And now that I have it written out like this, going back up to the original equation, you can see that that's exactly what we have on the left-hand side of this thing. We have 2x plus y squared, which was, coming back over here, 2x plus y squared, which was psi sub x, that's this term, oops, this term right here, plus d psi dy, the partial derivative of psi with respect to y, which was this term, 2xy, indeed 2xy, times y prime, times y prime. So this is how you take basically a full derivative of a function that involves multiple variables. There's kind of different ways to think about it, but basically this is just essentially chain rule, if you want to think about it. Ultimately, where this comes from, so all we're going to do here is apply chain rule. So if this result that we got down here looks scary, just think of it. We're taking the derivative of psi with respect to x, but by chain rule, you can think of it as psi is also a function of y. So we're going to have to take the derivative of the whole thing with respect to x, and we're going to have to take the derivative of the whole thing with respect to y times dy dx. So this has to do with chain rule. You'll see this again more in Calc 3. So again, if you've only taken Calc 2 and this step from here to here is a little uncomfortable for you, it's because it's something that you cover in Calc 3. And so let me just leave it at that. It's essentially an application of chain rule when you're dealing with a function of multiple variables like we have here. So long story short, d psi dx, the full, what we're calling a full derivative. So this is called the full derivative. And it's a full derivative, again, because ultimately everything that psi depends on, both x and y, both in turn depend on x. And so we can take the full derivative with respect to x in this case. Okay, whew. So this is the idea. If we apply this, applying this to that example, and again, all you need to know for this class is to get comfortable computing this type of a derivative, to just make sure. You don't need to understand all the ins and outs because that's a topic for Calc 3. But for now, we'll just focus on how we compute the derivative. So what does it look like to take the full derivative of our psi? d psi dx. So d dx of, make it totally clear, what was the function we were using? I've got it way back up here. X squared plus xy squared. Where again, we've got to keep in the back of our mind as we do this that y is a function of x. So what happens when I take this derivative? In fact, to make life easier, let's just make that totally explicit. Y of x squared. Make it totally clear that y depends on x. So let's take this derivative with respect to x. What happens when the derivative hits this first part? No problem. We're taking the derivative of a function that only involves x with respect to x. What's the derivative of x squared? That's simply going to be 2x. What happens when the derivative hits this next part? Well, it's going to be a product rule problem because I have x times some function y of x that is in fact being squared. So we've got a function of x times some other function of x, and we need to do product rule. So what we would do is this next piece, d dx of this whole big mess, x times our y of x squared term, means that I need to do the first times the derivative of the second plus the second times the derivative of the first. So let me just copy what we've already got. I've already got that piece. What is the derivative here of this piece? So first times the derivative of the second. So what is the first? I've got that times the derivative of the second. What is d dx of our y of x squared term? Well, that's going to require a little bit of extra work, so we'll come back to that in a minute. So first times the derivative of the second, plus the second, which is going to be our y of x squared term, times the derivative of the first. What's the derivative of x with respect to x? It's just 1. So first times the derivative of the second, plus the second times the derivative of the first. That is this derivative. Over here, though, I can't take the derivative with respect to x of a function that is called y. Right? I don't know how to do that. So what we have to do instead is change this, again, using chain rule. So I've got my 2x plus x times d dy of this y squared term, and I'm going to drop the x dependence, times dy dx. So by combining the differential and splitting the differential here, we've got d dy times dy dx. If you were to multiply those together, the dy's would cancel and we would get the net effect of that is d dx. So this is hopefully something you remember from doing chain rule when you're doing implicit differentiation. So hopefully this is making sense when it comes to implicit differentiation. And then the second term that we have here is just our y squared term times 1. And I'm going to, again, start leaving off that x dependence, so plus that extra y squared term. So what does it all look like? Let's move the pieces that we've already computed together. I've got 2x plus y squared plus x times this term. What is the derivative with respect to y of y squared? That's simply 2y. And we've got our dy dx. And so when we finally clean it all up, 2x plus y squared plus 2xy times y prime, that is the result that we've got here. So this isn't our solution to the original differential equation, and we haven't talked about where on earth we came up with this guess for psi anyways, but we'll talk about that in a minute. But how does this relate to, again, the solution of the original equation? Notice what we've found here. This whole thing here is the left-hand side of the original ODE. And so let's just rewrite that to remind ourselves what we're looking at. So we want to solve the following. 2x plus y squared plus 2xy times y prime equals 0. That is the original equation I have written way back at the beginning. We've just shown that the full left-hand side here is the result of taking the derivative with respect to x of this function psi. So this whole thing right here is d psi dx. So if we can figure out the psi for which this is true, and again, in the case that we just did, it was just given to us, but we'll talk about how we can figure out what psi is in a minute. All we have is a simple differential equation that looks like this. D psi dx equals 0. How would you solve that? So if we can find psi, then we have a simple ODE that we've got sitting right here. How would I solve that? Literally just basically integrate both sides, if you want to think of it like that. So we've got, it's separable. You can multiply both sides by dx if you wanted to. So we'd have the integral of d psi equals the integral of 0 dx. What's the integral of 0? It's just some constant. What's the integral of d psi? It's just going to be psi. This is the solution to that differential equation. So if we can figure out what psi is, then psi equals a constant is going to be the solution to this differential equation right here, which we just said is the same as this differential equation right here. So the hard part is finding psi. And then if we can find psi, such that the full derivative of psi, when we take the implicit derivative of psi, we get the whole left-hand side of our differential equation here. Then the solution to that differential equation is simply psi equals a constant. And so this is going to be the form of our solutions once we're able to find psi. That's going to ultimately be our solution. Okay, so this is kind of a mess now that we're looking at all of this. So let's just kind of review quickly what we talked about. We're given a differential equation that's going to be ugly, messy, right? Nonlinear, not separable, not easy to deal with. We move everything to one side of the differential equation, in this case the left-hand side by conventional, just always move it to the left. So all we're left with is a 0 on the other side. And our goal is to see if we can figure out a function psi where when I take the full derivative of psi, the full implicit derivative, when we implicitly differentiate psi, we wind up with the left-hand side here. And if we can find such a psi, and in this case it was just given to us, we'll talk about how to find it in a minute, then the solution to the differential equation, after all it's said and done, once we can find that psi, tells us that this really, the left-hand side really just looks like d psi dx equals 0. How do we solve this differential equation? That's straightforward. We can just basically separate the variables, integrate both sides, and this is what the solution looks like. So the hard part is finding psi. So let's think about how basically we got from psi to our differential equation. And if we can figure out how we get from psi to our differential equation, maybe we can figure out how to reverse that, how to get from our differential equation back to psi. Okay, when we took the derivative of psi, so recall what we just did. When we took the derivative, d dx, the full derivative of psi, which is a function of x and y, so let's do it like this, we wound up with the following. By chain rule, using chain rule and implicit differentiation together, we wound up getting basically d psi dx times dx dx plus d psi dy times dy dx. So this is what that derivative looks like. And this is what we tried to make be equal to the left-hand side. So notice this term here, again, I know we've already written this down, but this term here, this is our partial derivative of psi with respect to y. This term here is our partial derivative of psi with respect to x. This is just 1, and this is our y prime term. And so what the whole thing looks like is simply psi sub x plus psi sub y times y prime. So if our equation can take this form, where this is the left-hand side, then we'd have the following. We'd have psi sub x plus psi sub y times y prime equals 0. This is the original differential equation that we're trying to solve. So let's talk about go back to the original equation, because it turned out to be in this form. So going way back to the original differential equation, we kind of have these two different parts here. We have these parts that are sitting by themselves over here, and then we have this second part that's multiplying the y prime term. So I want to relate this part and this part to the two parts that we just found sort of generically down here. We have the part sitting by itself and then the part multiplying the y prime term. So let's talk about generically. So imagine we have an equation that looks like this. Of the form, let's call it m of xy, some generic function that can be a function of both x and y, plus n of xy times y prime equals 0. And note that this may also be rewritten. So you may also see something of the form, something where the differentials are split. So instead of seeing y prime, I would multiply the whole thing by the dx in the denominator of the y prime. And you may see this written as m of x comma y dx plus n of x comma y dy equals 0. So this equation here and this equation here are equivalent. All I would need to do is take this one and divide by the dx, and we would wind up with what I've got sitting right over here. So you may see these exact equations written in either form, as I've talked about before, with the differentials split or with them explicitly grouped together and writing out the y prime by itself. Okay, so if this is just some generic equation, we have some piece sitting by itself, some other piece multiplying by the y prime, and we can relate it so that this function or this equation here winds up pairing up and matching piece by piece with this equation up here. And we can find the psi such that these things match up. So our goal is to find we have an equation of this form where, to make everything match up, the m term, the m of xy, must be the term that matches this. It must be equal to this x partial derivative. And the other term, the n of xy, must be related to this term in front of the y prime. So that must be the y partial derivative of psi. So if we've got all of these, that makes this thing exact. Oops. Let me do a period here. Then the equation is exact. This is how we define an exact equation. And the solution is psi equals a constant. So this is our goal. Again, if we see an equation of this form, our hope is that this term here is the result of taking the x partial derivative of some function psi, and that this term here, the coefficient of the y prime term, is the result of taking the y partial derivative of that exact same function psi. And our goal is to find the psi in all of this. Okay, so how do we know if this is going to work? How do we know that such a psi exists? Well, just looking at it, we don't, but there is something we can do to check. And again, this is a topic from Calc 3. So you've seen that we've taken partial derivatives of this function psi. We can take a derivative with respect to x, where we treat y as a constant. We can take a derivative with respect to y, where we treat x as a constant. But what happens when we start to take more than a first derivative? What if I wanted to take a second derivative? Well, same thing can happen. We can have higher derivatives, and we can do them with respect to the same variable over and over and over. So I could have psi sub xx would be the second derivative with respect to x. I could have psi sub yy would be the second derivative with respect to y. Again, just notationally, we're indicating that by having extra x's or y's down in the subscripts. But we can also take what's called a mixed partial derivative, where we take a derivative with respect to x and then y, or y and then x. So we can check the mixed partial derivatives. And again, if you've taken Calc 3, this will make sense. But basically what I'm saying is, it turns out that when you take the derivative, the partial derivative, I should say, the partial derivative of a normal, continuous, well-behaved function, so all the functions that we're interested in, so I'm going to leave this part off, but we can take the partial derivative of a function with respect to x, then y. So x first, take the derivative with respect to x. It'll give you some new function. Take the derivative of that resulting function with respect to y. So x first, then y. You get the same as doing y, then x. So the order doesn't matter. This is one of a big theorem in Calculus 3. And again, there's some conditions on what types of functions this works for. They have to be basically continuous functions, sufficiently well behaved, the partial derivatives have to exist, yada, yada, yada. But basically what I'm saying is psi sub xy is how we'd indicate this first partial derivative that I just talked about. So psi sub xy would mean I'm taking the derivative of psi with respect to x first, then y. That gives you the same result as if you did the partial derivative with respect to y, then x. So this is the idea. If there's a function psi that exists, this will be true. So if such a psi exists, and again, our goal is to find psi, then the mixed partial derivatives should be the same. What this means, though, is if we remember, this is basically saying psi sub x first, then we'll do the y derivative of that should be the same as taking the derivative psi sub y, and then with respect to x. But what were these two things equal to? What is psi sub x? Well, if we come back up to here, psi sub x was supposed to be equal to this term sitting out here in our differential equation, our m term. So this is really m sub y. And our second term, psi sub y, if we come back up here, that was the n term. That was the term that was supposed to be sitting multiplying the y prime term. That's what n was. So psi sub y is n. And the remaining derivative that we haven't taken is this x. Right, so basically I replaced the stuff in the parentheses in these two locations with m and n respectively because that's how they were defined up here, assuming we can find such a thing. So if this is true, then psi exists. So if I can check the mixed partial derivatives of the unknown function psi and they're equal, then psi must exist. But I can do that by just assuming that it exists and recognizing that the psi sub x must be m, psi sub y must be n, and then checking their respective mixed derivatives. If they're equal to each other, then psi exists. And we're going to be able to find it. So this is the idea. I'm going to write a big, ugly theorem now that's going to kind of try to put all of this together. And then we'll actually come back to the example that we just did where we guessed psi a minute ago, and we'll talk about how we can find psi. We'll verify that this is true for that function, and then we will actually try to find psi. And then we'll do some more examples. And once you do examples, this will make so much more sense, I promise. So let me write this as a theorem. Oops. Don't need to zoom in that far. Good enough. Okay. So here's our big theorem related to exact equations. I'm going to let those two functions be nice, well-behaved, the m and the n. So I'm going to let m of x comma y and n of x comma y be well-behaved functions. In plain English, in the book, they give you a technical definition. So basically, well-behaved functions means, as far as I'm concerned, continuous with continuous partial derivatives. I guess I can just toss that in here. Then m of xy comma dx, or times dx, plus n of xy times dy equals 0. Or alternatively, let me write it the way that I normally will write them and that I think is more common. So again, taking that same equation and dividing by dx, you get dy over dx equals 0. These two equations, which are interchangeable, right, same thing. But then that equation is exact. Assuming, if I can write exact equation, if and only if m sub y equals n sub x. Okay, so this is the theorem that summarizes when we're going to be able to, when we have an exact equation that the solution method is going to work for. We just need my to be equal to nx. We need to take the derivative of this part with respect to y, take the derivative of this part with respect to x, and check and see if they're equal to each other. And if they are, then it means that basically the mixed partial derivatives of our unknown function psi are equal, and therefore psi exists. Okay, so to determine psi, let's think about what we know. The assumption is going to be the following. Basically, we said that what we were going to call psi sub x, that's going to be the m, and what we called our psi sub y, that was our n. And we can use this to try to figure out what psi is, right? So the assumption is some psi exists where this equation right here is the result of taking a full derivative. So a full implicit derivative of psi. And when you look at that implicit derivative, this first piece is the derivative with respect to x, and the second piece is the derivative with respect to y of the original function psi. So basically, the argument is that m is equal to psi sub x, that's exactly what we have written here, and n is equal to psi sub y, and that gives us something of the form of an implicit derivative that has been taken all the way. So this is the assumption that we've made. Notice the derivatives are different here. We're basically taking the derivative of m with respect to y, because that would make it be psi sub xy, and checking to see if it's the same as n, the derivative of n with respect to x, because if I took the derivative with respect to x on both sides of the equal sign here, I'd have psi sub yx. And that, again, goes to a theorem in Calc 3 that says the mixed partial derivatives psi xy and psi yx should be equal to each other, assuming you have a continuous function with continuous partial derivatives, a well-behaved function. Okay, so basically, these two equations right here come from assuming that we've got a setup that looks like this, that is the result of taking a full implicit derivative of psi. This being the derivative with respect to x part, this being the derivative with respect to y part. And we can use this to now back out psi by trying to solve these two individual, relatively simple differential equations. You'll notice these are differential equations. We have essentially a derivative equals to, in this case, some function that involves potentially x and y. So how do we solve for psi? Well, I can use this first one. If I want to get a guess for psi, I need to undo the x derivative. So what do? I integrate psi sub x with respect to x to undo the derivative. But I have to do the same thing to both sides of the equal sign. And this will give us, on the left, when we integrate this, the integral will cancel with the derivative, and we'll be left with psi. So I'll get that psi is equal to the integral of m dx. We can do the same thing here, and it's going to be important to do both to get another guess for psi, because this one potentially isn't going to have everything that we need, and I'll talk about that in just a minute. But basically, let's do the same thing down here. Psi sub y, I need to integrate both sides with respect to y. So that's the integral of n with respect to y. And when we integrate the left-hand side, The integral with respect to y will cancel the derivative with respect to y, and we'll just be left with psi. And on the right-hand side, we'll have the integral of n dy. But think about what happens when we integrate. There's something I left off in both of these, and it's a constant. So I'm going to have plus c1, and down here I'm going to call it plus c2, because they're potentially different constants. But here's a tricky thing. They're only constants with respect to the variable that we integrated with. So in this case, we integrated with respect to x. So this is definitely a constant as far as x is concerned, but what were we just saying earlier? Y, anything that involves y, as far as x is concerned, is also going to be treated as a constant. So this can technically not just be a constant, but can instead be a function of y. Similarly, down here, we integrate with respect to y, so this is a constant as far as y is concerned, but that could still mean it could potentially be a function of x. And this will give us two different guesses for psi, and we can kind of compare them together to figure out what our best guess is for psi. And we'll talk about how we can do that. If you continue and take additional math classes, a term you may hear, and I'm not going to go into any more detail than just giving you this term. So in this case, psi x is something called a potential function. And this is something you might see if you go on and take like a fluid dynamics course or an electrodynamics course. You will see these types of potential functions, and they're very common in physics. But this is the mathematical representation of what that might look like. Okay, so let's go back and kind of revisit this. Let's zoom out and see how much we've written here, and we haven't even done an example yet. Okay, so here's our giant mess so far. Look how much we've gotten through. Okay, this was all at the service of trying to get a handle on this differential equation. So here's our original differential equation, and here is what turns out to be the psi that solves this differential equation. If we set psi equal to a constant, we get the solution to this. So let's figure out, going through all of this process, let's kind of practice everything we just looked at in the context of that example. So, example. Let's just redo the one that we just did. And verify, in going through it, that everything works out the way that I'm claiming it should work out. So the original equation was 2x plus y squared plus 2xy y prime equals 0. And the first thing we need to do is assign m and n to these two pieces. So we said that this is going to be what I'm going to call my m, and this is going to be what I call my n. And we now have m plus n times y prime equals 0. Let's check if it's exact. The idea, again, if it's exact, is that this part here comes from having taken the x derivative of our unknown function psi. And this part here comes from having taken the y derivative of our unknown function psi. And so we want to basically check if psi xy is equal to psi yx, remembering that this term here, what we're calling m, is supposed to be the result of having taken the x derivative. So this is really m sub y equals n sub x. So you don't actually need to ever write this part down. I'm just trying to tell you where this equation comes from. We're assuming this is the result of having already taken the derivative with respect to x, and this is the result of having already taken the derivative with respect to y. And so now we're going to look at the mixed partial derivatives. This one still needs a y derivative, this one still needs an x derivative for our mixed partial derivatives. So let's check. What is m sub y? M sub y is simply going to be d dy. Let me write it a little, and again, partial d's, but I won't take off points for this in this class, so you don't need to worry about which symbols you use in this class. But if you're comfortable with the symbols from Calc 3 and they make sense to you, then please use the correct ones. But I won't take off points. Okay, so I want to take the y derivative of m. Here's m, here's the y derivative. What is the y derivative? Well, x, as far as y is concerned, is a constant. So when I take a derivative, this term is going to 0. What's the derivative of y squared with respect to y? This is simply going to be 2y. What about n sub x? Well, that's the derivative with respect to x of the n term, which is 2xy, just copying from the original equation. As far as the x is concerned, this y is a constant, the 2 is obviously a constant, and we're just taking the derivative with respect to x of x. So what's the derivative of x? What is this whole result going to be? Well, we'll get that 2y times a 1 for the derivative of dx dx. And indeed, these two things are equal. Equal. So the equation's exact. Right? This was our theorem. If this is true, if my equals nx, and this is how we've defined our m and n, then the equation is exact. So we've got an exact equation. All we need to do now is instead get our guess for psi. So what are our guesses for psi? Well, one of our guesses for psi comes from this piece. We know that this is supposed to be the result of having taken the derivative with respect to x. So on the one half, I have that psi sub x is equal to our m term, which again implies that if I integrate psi sub x with respect to x, it's the same as integrating m with respect to x, we should get psi. And let's plug in now for what our m is. It's going to be 2x plus y squared. So I'm needing to integrate the integral of 2x plus y squared with respect to dx. So there's one way we're going to get a guess. The second way comes from recalling that this term is supposed to be the result of having taken the derivative of psi with respect to y in our big implicit derivative. And so that is what n is equal to. And similarly, if we integrate both sides of psi sub y, but this time with respect to y, integrate n with respect to y, we'll get another guess for psi. And in this case, it's the integral of our n term, which is 2xy, with respect to y. So let's do these integrals over here. Let's come zoom in on them. What is the integral of this term with respect to x? So what's the integral of 2x with respect to x? Well, that's not too bad. That's going to be x squared, right? The integral of 2x is x squared. What about this term? What's the integral of y squared with respect to x? Well, again, all we need to remember is that as far as x is concerned, this y squared is a constant. So what happens when you integrate a constant? What happens when I integrate the number 3? I get 3x. What happens when I integrate y squared? I get y squared x. Plus something that is potentially some constant, or it could potentially be a function only of y, as you'll recall. Because again, we integrated with respect to x. So we get a constant, but that constant could be a function of y. It's only a constant with respect to x. And then down here, similarly, we'll find our guess for y, or for psi. What is the integral of this piece with respect to y? Well, in this case, as far as the whole thing is concerned, the 2x, that's a constant, right? So the 2x is a constant. We just need to integrate y. What's the integral of y with respect to y? Well, that's 1/2 y squared. So we're going to get 2x times 1/2 y squared, plus some other thing that could either be a constant or potentially a function of x. And if we clean these up and compare them, right, this term here really, when I cancel the 2 and the 1/2, this is just simply xy squared. And so what we can see is as I compare these are both supposed to be guesses of psi. They should be giving me the same thing. What I see is that this first piece, let me do this with color, this term that's xy squared, Well, I have an xy squared in this function as well, so that definitely shows up inside. This term and this term are really the same thing. But what about this term? I have an x squared term by itself here, but I don't have an x squared term here. What I do have, however, is this unknown function of x. Well, here I have a function only of x. Here I have something that I didn't have enough information in this because we took the integral with respect to y. All I knew is I could wind up with something that could be a function of x, but I didn't know what it was exactly. And it turns out it must match that piece right there. And then this last piece is something that's just a function of y. I've used up all the pieces down here. There is nothing that showed up that's just a function of y. So this must not ultimately match to anything. So we could have just plus some other, constant down here. This one could match to. And it could literally be plus a 0 as far as we care. Doesn't really matter. So we've got to put the pieces together. So looking at this, we find that our function psi is equal to, we said it has an xy squared term that showed up in both, and it also has this x squared term, so it must be x squared plus xy squared. And it could have some other constant, but again, we can always leave off that additional constant because the solution is going to be psi equals a constant, and I could always take the constant from the left-hand side and roll it over into the right-hand side. The solution to the original ODE is psi equals a constant, or to make it totally explicit, x squared plus xy squared equals a constant. There is our solution. And again, why is psi equals a constant the solution? That has to do with if we go way back to right here. There it is. The fact that if we can write the left-hand side as the result of taking d psi dx, then we get a differential equation that can be integrated and solved very easily right here. So that's why psi equals a constant is the solution. So once we find psi, we're good to go. Okay, so this is the solution to this exact equation. And this is the process when it actually comes time to do an example on the homework and so on and so forth. This is the process that you should be doing. It should only take about this much room. So let's do another one from scratch. Let me find one that I've got here. Okay, let's try this one. This looks as good as any. So I'm going to write this one as the following. So we've got e to the x sine of y plus 3y plus 3x plus e to the x cosine of y dy dx, where it's this whole term that's multiplying the dy dx, and that's going to be equal to 0. So the first thing we do is we get it into the form that we were talking about, and luckily this one's already written in that form, but if this had been moved over to the other side of the equal sign, just rearrange it so it's in the form where we've got some stuff plus some other stuff times dy dx equals 0. So we've got our first stuff plus our second bit of stuff times dy dx equals 0. The first bit of stuff, whoa. Sorry about that. Touch screen getting finicky here, I guess. That first term is m. The second term, the stuff multiplying dy dx, that is my n. So the first step is to check to see if it's exact. And the step to check if it's exact is I check to see if the y derivative of this stuff matches the x derivative of this stuff. So m sub y equals n sub x. Is that true? So what is m sub y? Well, that's the y derivative of this big mess. So dy of e to the x sine y plus 3y. And we're going to check to see if that is equal to the x derivative of this n term. So n sub x is d dx of 3x plus e to the x cosine of y. So let's see what we get for each of these. What is the y derivative of this? Well, as far as y is concerned, this e to the x is just a constant, so it's just going to get sifted out of the derivative. And we just need to look at what is the derivative of sine of y. So what's the derivative of sine? The derivative of sine is cosine. So in this case, we get times cosine of y. Plus, we also need to take the derivative of this 3y term. So what's the derivative with respect to y of 3y? That's simply plus 3. So here's our m sub y term. Now let's check our nx term to see if it gives us the same result. So coming over here, we'll take the derivative with respect to x. What's the derivative of 3x with respect to x? Well, that's 3. What is the derivative of e to the x cosine y? Well, as far as x is concerned, cosine of y is a constant. And so we just need the derivative of the e to the x part. What's the derivative of e to the x? It's e to the x. And again, that cosine y is just a constant. These are the same, so it's exact. Okay, so we've found an exact equation. What that tells me is that that function psi that we're looking for definitely exists. And I know that this part, the m term, is the result of taking the x derivative of psi. So I know that psi sub x is equal to the value of m that we found. So, and again, I'm going to kind of skip some steps here and just write. If we were to integrate both sides of that with respect to x, we would find that psi is equal to the integral of m dx. And what does that give us? So in this case, that means that psi is equal to the integral of this m that we found here. So that's e to the x cosine, oops, not cosine, e to the x sine of y plus 3y. And again, we're taking the integral with respect to x. So what do we get out of this? Well, again, as far as x is concerned, the sine of y is a constant, so I just need to integrate this e to the x term. What's the integral of e to the x? It's just e to the x, so I get e to the x sine y. And then I also need to integrate this term. What's the integral of 3y with respect to x? Well, this is just a constant. When you integrate a constant, you just get that same constant times x. So plus 3yx, I'll write it as 3xy, plus something that can potentially be a function of y. So here's our first guess for psi, right here. Let's get our second guess for psi and try to reconcile the two. So our second guess comes from knowing that this portion of the equation, right here, must be the result of taking the derivative of psi with respect to y. And if we integrate this with respect to y, it'll give us our guess for psi. So psi must be equal to the integral of n dy, which would give us that psi is equal to, copy down what n is, 3x plus e to the x cosine of y. We're integrating that with respect to y. So what's the integral of this first term with respect to y? Well, it's a constant as far as y is concerned. So when we integrate a constant, it's just that constant times y in this case. That'll just give me a 3xy. This second term we're also integrating with respect to y. So the e to the x, as far as that is concerned, it's a constant. It'll just sift through the integral, so we'll have an e to the x term. And we just need to know what's the integral of cosine of y. Well, the integral of cosine is sine of y. And then again, we could potentially get some portion of this that's either a constant or something that's just a function of x because we integrated with respect to y. So we've got our two guesses for psi. They're sitting right here. We should go through and kind of match things up. This piece clearly matches this piece. This piece matches this piece. And these pieces don't need to match anything, right? They could both go to presumably a plus 0 here, a plus 0 here. They could be constants as far as we're concerned, but there's certainly no function x or y for them to match up to. So we can ignore all of these parts. They don't have anything they need to match up to make things work. And we can just write that psi is equal to 3xy plus e to the x sine y. And the solution is psi equals a constant, or if we were to write that out explicitly, 3xy, and I say explicitly, it's still going to be an implicit representation. So 3xy plus e to the x sine y equals a constant. There is our solution, our implicit solution. As good as it's going to get. Okay, so this will be the routine. It's much harder to understand the principle behind it, but once you understand that really the idea is we're trying to make the equation look like the result of an implicit differentiation. And so we're doing backwards implicit differentiation, basically, to try to get our solution. There's some function psi. This is supposed to be the result of taking the derivative of that function psi with respect to x. And we get a portion that's the partial derivative with respect to x, plus, by chain rule, the d dy dx term over here. And this is the d dy part, so the y derivative part. You can verify that the mixed derivatives are equal to ensure that such a psi exists, and then you can find that psi by going through the process that we've done here, integrating this piece with respect to x, this piece with respect to y, and comparing the two results to find all the common pieces and kind of filter through it that way. Okay. I know this video is probably already droning on, but I want to talk about one additional thing that can happen. What if we have an equation that looks like, so what if the equation, let me zoom back in so I can, it's bad handwriting, whatever, you can read it. What if our m of xy plus n of xy dy dx equals 0? So what if we got our equation that looks like this and it isn't exact? Meaning, what would be true? It would mean that we checked if my equals nx, and they turned out to not be equal. So what do we do in this case? We're running out of viable techniques. It turns out we might be able to fix it. We might not be able to fix it, but we might be able to change this. With an integrating factor. So what we're doing is basically combining this new exact equation technique with the integrating factor technique that we learned in the previous section, sort of combining them together into a super technique. But we're, again, getting into very specific cases. So we've got an equation that looks like this right here, and it turns out that it's not exact. There is no equality between our m sub y and our n sub x. Is it possible to find a function that we can multiply the whole equation by that will modify our first term here and our second term here in such a way that this will become true, that the derivatives will be equal to each other when I look at the derivative of the first piece and the second piece? Okay, so this is called integrating factor combined with exact equations. I'll just write it as integrating factor for exact equations. And again, this is going down the rabbit hole with this technique here. So you'll have some of these on the homework. This would probably be, well, I don't want to guarantee I wouldn't put it on exam, but probably not. So we'll maybe talk about that at exam review time. So let's not worry about that for now. But this would certainly be a mean question for me to put on an exam. But let's go through how the process might work to set up one of these things. So can we find an integrating factor? A mu of xy, so let me call it an integrating factor. Find an integrating factor. mu of x comma y such that when I multiply the whole equation, we get mu of xy comma n, or times m of xy plus mu of xy times our n of xy times dy dx. Still going to be 0 because 0 times this mu is still 0, so we don't need to worry about that. Can we make it so that this is exact? So we'll call this some, I don't know, maybe I'll use just lower cases. I don't know what our book does. I'm going to call this lowercase m and this one lowercase n, the modified versions here, and check and see if this is exact. So is my equal to nx on the lowercase modified versions where we've multiplied through by mu? Right, that's our goal. Right, so essentially all we're saying is I want the y derivative of this whole mess to be equal to the x derivative of this whole mess, and we would have an exact equation. It would just be an uglier equation than the one that we started with. Right, so again, as long as the y derivative of the first chunk matches the x derivative of the second chunk, we're good to go. And I've just renamed the chunks to lowercase m and lowercase n to correspond to the modified versions of the original m and n. I hope that makes sense. Okay, so let's check. What would this mean if we actually took the derivative? So that means I'm taking the y derivative of this whole mess here. So basically I'm saying d dy of mu of xy m of xy, is that equal to d dx of the n term, which is mu of xy times the capital N of xy. Well, when I take these derivatives, let's actually evaluate these derivatives out as much as we can, given that these are unknown functions. But when I do these derivatives, because in this case, both are functions of y, in this case, both are functions of x, this is going to require us to do product rule, because we have a product of two functions. So when I do product rule over here on these, I'm going to get first times the derivative of the second, and I'm going to stop dropping the parentheses x, y's. Just know that mu, m, and n all depend on both x and y, but this will make things a little bit cleaner. So let's take our y derivatives over here. That means by product rule, we're going to have first times the derivative of the second, so it'll be, whoa, let's undo that. Really getting choppy here. Come on, touchscreen. Okay, hopefully this goes better. So first times the derivative of the second plus the second times the derivative of the first. So mu sub y times capital M. This is the result of product rule of this. So first times the derivative of the second, first times the derivative of the second, plus second times the derivative of the first, second times the derivative of the first. And doing the same thing on the other side, but with x's, we'll have first times the derivative of the second plus the second times the derivative of the first. So here's what we are checking to see if these are equal. We can clean this up a little bit. I'm going to group the mu terms together at least and factor them. So I'm just going to, this next step is just pure algebra. I'm going to factor out the mu. I'm going to have the my minus an x term that I would get by moving this term over to the left and then factoring the mu out. And then I'm going to just move this term over to the other side. So on the other side, I'll have mu sub x times n minus mu sub y times capital M. Okay, so here's our equation, just algebraically rearranged. Let's think about what we've got here. What are we even trying to solve for? Both m and n are presumably given in the original equation, right? They're part of the original equation. So that's not what we're interested in. What we're interested in is finding this integrating factor. We need to solve for mu. And if I look at mu, it shows up in three places. Here it is by itself. Here's the x derivative of mu, and here's the y derivative of mu. The fact that I have both an x derivative of mu and a y derivative of mu, meaning that basically mu depends on two independent variables, both x and y, tells me that this equation is a partial differential equation, not an ordinary differential equation. So all that means is we have derivatives with respect to more than one independent variable, right? So derivatives with respect to more than one independent variable. And that makes this a partial differential equation. We definitely aren't solving that in this class. So instead, if we look for a mu that is a function of only one variable, so instead of having mu be a function of both x and y, if we can get lucky and have it be a function of only x or only y, well, then one of these derivatives wouldn't even show up, right? It wouldn't make sense to take a derivative with respect to y if it's only a function of x, and we could get rid of one of these terms. So here's an if, a big if. If we can write mu as a function of one variable, then this would be an ODE that we could solve. So basically, we're using differential equations to get the factor that we need to solve the differential equation. This is what happened when we did integrating factor as well. It's how we found the integrating factor. We kind of guessed at something and we found some requirements on mu that wound up taking the form of a differential equation that was separable that we could solve in order to figure out what that function mu should look like. And then we use that function mu to then solve the parent differential equation that inspired the whole problem to begin with. Okay, so in this case, let's just say it's going to be a function of x. Let's try mu of x. So it's just a function of x. How would that change things? In that case, we'd come back up here. M and n are still both functions of x and y. It's only the mu that we're changing to say that it is only a function of x. So if this were the case, we would still have the same right-hand side. Right? Nothing would change other than the fact that this only depends on x now. And on the right-hand side, we'd have this term, but what would happen to this term? It would be gone, because basically we wouldn't have had to do product rule up here, because we only have a function of one variable. So long story short, we can get rid of it more easily like this. Just say mu sub x times n, and this minus the other term would wind up just being minus a 0, because mu sub y is 0. What happens when I take a derivative of this function with respect to y? Well, it has no dependence on y. It's a constant as far as y is concerned, and therefore its derivative would be 0. So this is the idea. And now I've got an ordinary differential equation here for mu, as long as this big mess gets some nice cancellation. So let me rearrange things. Again, let's just do a step of algebra to solve for mu sub x. So basically I would get d mu dx, which is our mu sub x. Let's write it. Yeah, that's fine. So d mu dx, which is this term, and I'm going to divide everything by n, is equal to mu times my minus nx over n. This is an ordinary differential equation where x is the only independent variable under the assumption that over here, this big mess winds up being only a function of x. So if we get lucky, and this my minus nx over n term is only a function of x, then we can solve the ODE. And we would solve it in the same way that we solved for integrating factors back in the previous section. Because it would make this, if it was just a function of x, we would just have a linear first-order differential equation, right? It's linear because there's nothing wild going on with mu here, and it's a first-order one. We could use integrating factor to solve it. Okay. So Let me make that clear. Then we can solve the resulting linear first order ODE for mu. And once we have that mu, we go apply it to the original equation, and then we still have to solve the original equation using the exact equation technique. So all this work is just to find a factor that we can multiply the original equation that we actually cared about by in order to make it an exact equation. And you still have to solve that part of the equation. So keep that in mind. We did, in this case, we presumed that mu is just a function of x. Alternatively, if we had assumed that mu was just a function of y, we would have had the same thing over here, but again, comparing here. Looking at this line, if we assume that mu is only a function of y, this would all be maintained over here. But it'd be this term that would go to 0 instead of this term. And we'd have a slightly different situation. The sign would be changed. And again, this term would survive instead of this one. And we would solve, and we'd wind up with a capital M in the denominator instead of a capital N in the denominator. And we could get the result that way as well. So let's just kind of, hopefully you can bear with me and just pretend that we have figured out this function over here. We got lucky, it's only a function of x, and we just solved using integrating factor because it's a linear first order differential equation. If we did that, what we would get are the following results. So let's do it for both, assuming mu is a function of x and mu is a function of y. And let's just do these as 2 bullet points to kind of summarize, because I think we've probably spent enough time on this. Okay, so if we wind up getting the following, mu sub y minus, m sub y minus n sub x divided by capital N, so the result that we just got right here, make sure that's right, I think that's good. If that is a function only of x, then our integrating factor is mu of x should be equal to e to the integral of my minus nx over n dx. And similarly, if instead we tried the other case, tried to make it all be a function of y instead, so if we got my minus nx over m is a function only of y, then the integrating factor that we would use is going to be mu of y, only a function of y in this case, and it's going to be equal to e to the integral of my, oops, I think I'm missing a sign here. I think I've got to flip the sign, because yeah, that sign would flip, this sign would flip. I think I need to flip these in order to account for the sign flip. Okay, so notice this sign, the order of these flipped compared to these because we needed to account for the different sign that we would get. Here, this term was positive coming from here, but if this had been the term that survived, it would have been negative, and we would have had a sign flip, and we can account for that sign flip by just switching the order of those two terms. Okay, I think that should do it. So these would be our integrating factors. So long story short, it's possible. It's obviously hideous. Let's do one example, and then we can finally be done with this method, because it's, again, going down the rabbit hole at this point. It's not going to be a common thing that you're going to encounter a ton of the time. Okay, so here's the equation. It's going to be y times x plus y plus 1 plus x plus 2y times dy dx equals 0. So here's our differential equation. And we start by assuming it's maybe an exact equation and seeing if we get lucky. So there's my m, there's my n. Is it exact? So I need to check if my, come on now, my is equal to nx. So what is m sub y? What is the y derivative of this? You can either distribute through and take the derivative, or we could just do a product rule. I'll just do product rule. So first times the derivative of the second, first times the derivative of the second, plus the second times the derivative of the first. So there's the derivative of the first, and there's the second. And what we get out of that is what? I'm going to get a y plus x plus y plus 1. So I'm going to get an x plus a total of 2 y's plus 1. I've got this y here, and then this y times this one here for a total of 2 y's plus just this 1x and this 1, 1. Okay, so there's my. What about nx? So what is the x derivative of this term? Well, that's pretty easy. This one has no x dependence, so the derivative of that term is going to be 0. What's the derivative of just x? It's 1. So we just get 1. Are those the same? Not equal. So not exact. Okay, and so now we say, okay, is there a way to make it exact? So is there a mu x or mu y integrating factor to make it exact? Is there something I can multiply the whole equation by to get it to work out? And again, the check that we have to do is just check to see if these combinations here and here wind up being functions of only x or only y. So let's check to see if either of these is a function of just one of those variables. So doesn't matter which order, just pick one. Let's check if the my, they're going to be easy because they're basically very similar. My minus nx over n is a function of only x. Okay, so get it all on the screen at once so we can do this. Where's my my and my nx? Here they are. My, we already computed. Nx, we already computed. So assuming I didn't screw those up, our numerator looks like x plus 2y plus 1 minus nx, so minus 1. And then we divide the whole thing by n, which was x plus 2y. And what do we get? Well, I have a plus 1 here, a minus 1 here. I'm going to get simply x plus 2y in the numerator. What do I have in the denominator? X plus 2y. What is that? It's equal to 1. It's a constant. That's definitely can be thought of as only a function of x. So constants are fine as well. Constant can be a function of only x, right? So we found it. The first case wound up working. We're going to be able to treat or find a mu sub x based on this. So again, if this hadn't worked, if we hadn't gotten either a constant or a function of only x, then we would have moved on to this. And basically, it would look the same. The numerator would look the same, but we'd be dividing by this term instead and checking to see if we got a function that was only a function of y or a constant. And if that was the case, then we'd know that we'd be dealing with a mu sub y term, and this would be what it looks like. So here it is. Here is what our mu sub x is going to look like. It simply needs to be e to the integral of whatever we just found for our mu y minus nx over n. We already found mu y minus nx over n. It was simply 1. So our integrating factor is a mu sub x equals e to the integral of, again, my minus nx over n dx. But we already found this quantity. It's what we just solved for right here, and it was 1. So this is simply e to the integral of 1 dx. What's the integral of 1? It is x. E to the x is our integrating factor. That's it. So go back and multiply the original equation. The original equation by e to the x. And I don't remember what our original equation was, so I'm going to zoom out so I can see it. But it just needs to take this whole equation multiplied by e to the x. So we're going to get e to the x y times x plus y plus 1 plus e to the x times x plus 2y dy dx equals 0. So here is our new equation. It's the same as the original equation. We've just multiplied by e to the x, which is totally fine. This one should be exact. All right. It should be exact because presumably all this giant mess of math that we went through had some meaning, and we've now got it set up so that our sort of what we're calling our lowercase m and our lowercase n will meet this requirement. That was the whole thing we set out to do that eventually led us to this differential equation that we had to solve. So we should be satisfying that because we solved that differential equation. So again, this thing should be exact. So we'll call this first part our lowercase m. We'll call this second part our lowercase n. And we should be checking, maybe I can see if I can cheat and make this look a little nicer. Almost. Everything but the letter D is going to come. Come on. Okay, good enough. Okay, let's clean this up so we can actually see these letters that I'm writing. All right, so this is what we're calling our lowercase m and n, as I referenced back up in the original equation, wherever the heck that was, back here. So this is our next thing we need to check, is my equal to nx. So our normal check for whether equation's exact or not. So we just need to check my and nx, see what we get. So what is going to be the y derivative of this big mess? It should be very similar to what we did before. We can kind of clean this up a little bit. So I'm going to get e to the x is a constant as far as that y is concerned. And so the y derivative, again, is going to be, we can do a product rule on this. So it's going to be e to the x times first times the derivative of the second. So first times the derivative of the second, plus the second times the derivative of the first, plus the second times the derivative of the first. And we get e to the x times what we got before, which was x plus 2y plus 1. Good. Now we need to check the x derivative of this one, and it's a little bit more complicated now. Because I'm taking the x derivative, this term, e to the x times x, is going to require product rule. So I'll do first times the derivative of the second, first times the derivative of the second, plus second times the derivative of the first, so plus x e to the x. And then for this next term, I'll have e to the x times 2y. As far as the 2y is concerned, that's a constant with respect to x, but the derivative of the e to the x is going to give me an e to the x. So I'll get 2y e to the x. And if we factor out an e to the x from this that shows up in all the terms, notice that I'll have a plus x, a plus 2y, and a plus 1. So an x plus 2y plus 1. And indeed, they're now equal. So it's exact. Okay, so it should have been exact, it was exact, and now we can solve for psi. Psi should be equal to the integral of the m term with respect to x, or equivalently, the integral of the n term with respect to y. And what do we get for this first one? This is going to be the integral of, again, go back and find my m term here. So here is what I'm trying to integrate. It's e to the x times y times, times x plus y plus 1 dx. And for our second one, it's going to be the integral of e to the x times x plus 2y with respect to y. Okay, so let's do these integrals. They don't look very pretty, but they shouldn't be too terrible. Let's call them 1 and 2 just to make them easier so I can do them in separate places down here so we don't run out of room. So let's start with number 1. I'm going to clean that up and write it as, let me distribute the y through and kind of break it up into some pieces here. I think we might be able to pull this off without as much trouble if we can get this squared away. Okay, so I'm going to distribute the y through, and I'm going to have the integral of e to the x times xy, and then I'm going to have e to the x times y squared, and then I'm going to have e to the x y dx. Okay, so I've distributed basically this whole thing through to all these terms. This is going to be the one that's a little tricky. We're going to have to do some integration by parts, but these ones are straightforward. All we need to integrate is the e to the x part, so that's going to be simple. So I'm going to rewrite this as the hard integral. I can pull the y out. Let's factor the y out in front because it's a constant as far as, again, the integration is concerned. But I have x e to the x dx. So this piece just matches this term with the y factored out. The rest of it is also going to be easy because it's simply going to be the integral of e to the x times y squared plus y, but as far as x is concerned, this y squared plus y could be factored out as well. And so for this first part, what we're going to do is let's let x be equal to u, dv be equal to, let's do all of these here. Let's write it how I normally write it. Okay. U equals dv equals du equals v equals. Hopefully I don't lose anybody. So u is going to be x, dv is going to be e to the x dx. The du term is then going to be dx, and v will just be e to the x, doing this integral and this derivative. And so the first integral will be x e to the x minus the integral of v du, so e to the x dx. So this is the result of working on this piece over here. And can't forget the big y that we had in front of everything. So there's the y to tack onto all of that. Okay, one part down. And let's do this portion of the integral, which is, again, going to be very straightforward. We really just need to worry about the integral of e to the x. What's the integral of e to the x? It's e to the x. And that's just going to multiply the y squared plus y term, as though the y squared plus y were a constant, plus some constant that can be thought of as, in this case, a function of y. So if we clean this all up, we've got xy e to the x for the first term. This integral is just going to be e to the x, so I'll have minus y e to the x. And then I've got this big ugly term. So I've got a plus y squared e to the x, and then a plus y e to the x, plus c1y. And notice that this piece here and this piece here can potentially cancel. And we'll really clean it up. Xy e to the x plus y squared e to the x plus c1 of y. So here's our one guess for what psi could potentially be. So here's one guess for psi. Now let's do the second integral, number 2. Second integral is this one right here. The integral of n dy, which we've already written right here. This one's going to be relatively straightforward. This is the only term that depends on y. So we've got the integral of, if I distribute through, it'll be x e to the x, but it's with respect to y, so that's easy. And then the second integral, well, I can just factor that e to the x outside again. It's just the integral of 2y dy. This one's very easy to do. What's the integral of this first one? Well, as far as y is concerned, this is just a constant, so I'm just going to get x, y, e to the x, right? It'll just integrate, dy integrates to a y. And then over here, I'll have e to the x. What's the integral of 2y? That's y squared. So plus e to the x times y squared, plus something that could potentially be a function of x. And so here's our second guess for what psi could be. And so if we compare these and find all the common parts, we get that psi equals, they both have an xy e to the x term, they both have a y squared e to the x, y squared e to the x, and then there's nothing for these two pieces respectively to match to. So it's just going to be xy e to the x plus y squared e to the x. And the solution to the ODE is that psi equals a constant, or more clearly, xy e to the x plus y squared e to the x equals a constant. Whoa, can't even box my answer. There we go. So that's our solution. It required us to do a lot of extra work. We had to try to fit it all on one page here. So this is a full page type homework problem if you wind up with one of these. It required us to come back up here, check if the original equation was exact, recognize that it wasn't. Check to see if we could make it exact by checking both this and the equivalent of this, but dividing by m instead to see if they were a function. In this case, this was a function of only x, or the other variation was a function of only y. Once we saw that it was, we knew what our integrating factor could be. We multiplied the original equation by that integrating factor, and then we were basically back to square one, checking if it was exact. Once we saw that it was, go through the math and solve for psi. So again, not something you're going to have to do a ton of. I do think I included maybe one of these on the homework, but probably not going to give you one of these on an exam, unless I want the whole problem to be the only problem on the exam. So good luck with these. They will make more sense as you start to do them. And we'll definitely review this technique a bunch more before the first exam. So don't freak out if you feel like you still need some time to kind of get it down. But otherwise, good luck on the homework. And we'll learn our final technique for solving first order differential equations in the next video.